All right, I'd like to talk about the rational root theorem. The rational root theorem tells us about what are potential rational roots of a polynomial. They don't necessarily tell us the exact rational roots, but they tell us what numbers might have a chance at being rational roots. So what do we mean by that? First, let's recall what it means for a number to be rational. So a number is rational. Well, what does that mean? So often when we think of numbers, we say, well, it's irrational, and then we say something about the decimals, right? We'll say, oh, it's irrational if it's never ending and it never repeats. So it's rational if it's eventually repeating. People like phrasing that in terms of decimals. But that's not actually the most useful way of phrasing it. And I think it's more useful, think about an equivalent form you've seen, where a number x is rational if x equals p over q, P and Q are integers, and Q is not 0. And when we see a number like this, right, a number like 2/3 or -3/5 or 1, 4. All right, why is 1 rational? Think about that for a second. Pause if you need to. All right, 1 is rational. I can write it just as 1 over 1. All right, so every integer is rational. I can put it over a denominator of 1. So rational numbers are nice, they're easier to understand. And one thing about them also is whenever we see a rational number, P over Q, we also have something we can do with this. We can put it in lowest terms. Right? So what we mean is that there's no common factor between the top and the bottom. Right? So 4 over 6 is not in lowest terms, but 2 over 3 is after I've divided out the 2 on top and bottom. Okay. And the rational root theorem, which we're going to talk about, tells us what potential rational roots there are. It doesn't necessarily, a number we get from this result isn't necessarily a root. But any rational root number that is a root has to be on the list we're going to get from this process. All right. Same way, a given list, if I list everyone who's eligible to be president of the United States, and I go through the qualities they need to be a US citizen, they need to be at least 35 years old, they need to be born in the US. All of those happen, right? That doesn't mean every single one of them is the president. Only one of them at most could be president. And there's similar criterion for who needs to be a senator or something like that. So we'll have a list that we'll get out of a process. And we're not going to do the whole process every time, but we'll look at what the result of that process is. So I want to show an example where we do the whole process out. That's the basic idea of what we wanted. That gives us this. So let's look at following polynomial. Three x cubed plus x plus 2. Now let's say we want to know what the rational roots are, the potential rational roots are of this. Right, so we'll write x equals p over q, and we'll assume p and q in lowest terms, and we'll plug that in here. So that's the same, and we'll assume that's equal to 0. Right? So it's 3, so we're assuming this is a root. So this is 3 p over q cubed plus p over q plus 2 equals 0. And now we'll expand that out. 3p cubed over q cubed plus p over q plus 2 equals 0. There are a lot of denominators floating around here. Those make life tough, difficult to understand. So let's clear them out. If I multiply by q cubed, clear out all my denominators because all just powers of q. And this side's already 0, so that side's going to stay the same. So we'll multiply by q cubed. That's the same as 3 p cubed, because the q cubed will cancel, plus 2 of the cubes will stay when we cancel the q. So plus q squared p plus, there are no q's in the bottom to cancel this term, 2q cubed, and q cubed times 0 is 0. All right. 3p cubed plus q squared p plus 2q cubed. Let's write that back up top, but hopefully we won't forget what our original polynomial is. I'm going to just copy it here, so I don't have to. 3p cubed plus q squared p plus 2q cubed. Okay. That's equal to 0. Now I want to do something. I'm going to pull out, I'm going to notice something. These two terms only have p's in them. This term does not. You can factor a p out and bring that term over. 3p squared plus q squared equals negative 2q cubed. And now here's the fun bit. P and q don't have any common factors, right? It's in lowest terms. So p and q cubed don't have any common factors. That's worth thinking about, why that's the case. But p and q cubed don't have common factors. So all of p's factors need to be in this, negative 2 or 2. So p must divide 2. I can do a similar argument with q. Every term up here has a p, so every term up here has a q except the first term. So 3p cubed equals negative, well, I'll put the negative in parentheses, but I'll bring these over and factor. Q negative q p squared, no squared there, qp plus 2q squared, minus. There we go, minus. If I brought these terms over and I factored out a q. Q and p don't have any common factor. So q and p cubed don't have a common factor. So q, if it divides this, has to divide 3. Right, just as p had to divide this, I had to divide 2. Q must divide 3. Okay. So that means we have a very short list of possible values for p and q. The divisors, p of 2 for p has to be plus or minus 1 or plus or minus 2. Q has to be plus or minus 1 or plus or minus 3. Those are the divisors. So now we can put that together. A total set of x must be plus or minus 1 over 1, plus or minus 2 over 1, or plus or minus 1 over 3, plus or minus 2 over 3. Notice that because I have a plus or minus up top, I don't need to actually worry about the plus or minus in the denominator. That will already be taken care of up top. So we now have a finite list I can check. And we can plug those back in if we want to our original polynomial, 3x squared, sorry, 3x cubed plus x plus 2. And for each of them, check if it's a 0. This is a good way of being able to check now only a finite list. We get to find all the rational numbers that are roots. This is also nice because we know a rational number is a root. We can use it to factor. Right? We've seen that before. Okay. So what's the general thing happening here? Well, if we go back to this polynomial, well, look. We had a 3 here. This became a 3 over here. We had a 2 here. This became a 2 over here. Right, they moved over. So something happened with the lead coefficient and the constant coefficient. And this lets us state the rational root theorem in the general form. And the rational root theorem says, if f of x is a polynomial, it equals an x to the n plus n minus 1 x to the n minus 1, n minus 2 x to the n minus 2, a1 x to the 1 plus a naught. Oh, I'm running over. Let's make my dots a little smaller. a1 x to 1 plus a naught. I guess I'll go to the next line. Hopefully we don't mind that. All right, so the idea here is I've written it in descending powers, a naught being my constant term, a0 being my constant term, right? And an being my lead coefficient. All right, so I've got a polynomial. And we're going to assume with integer coefficients. So all the ANs of integers. Okay. And assume that x equals p over q in lowest terms. Lowest terms is a root of f. Then p must divide a naught, a0, and q must divide an. All right, so our denominator has to be a divisor of the lead coefficient, and our numerator has to divide the constant coefficient. Let's do another example. Now, this is the statement of the rational root number. I want to do another example. All right. Let's say we have the following polynomial: 2x cubed plus 5x squared plus x minus 2. Now, if you want to find the rational roots yourself for a moment, pause, work out what you think the potential rational roots are, and then continue the video. I will give you a second to pause now. All right. So we're going to assume that the rational, we want to know what the rational roots are. Well, we'll assume x equals p over q, p and q in what are the lowest terms, right? And now p must divide 2, q must divide, actually also 2 in this case. Okay. P has to divide this number, q has to divide that number, but they're both 2. And now if we list our possibilities, these are going to become plus or minus 1. Well, first we'll note that what are the divisors of 2? Just plus or minus 1 and plus or minus 2. So our possible roots are plus or minus 1, plus or minus 2. These are the ones where our denominator is 1. And plus or minus a half, this is when our denominator is, numerator is plus or minus 1, our denominator is 2. Again, we don't need to worry about the negative denominators. We also get the pair plus or minus 2 over 2, but that's just plus or minus 1, so we've already got it. So our potential roots are these. And if we do the arithmetic, we'll actually find that actual roots, so actual rational roots here, are -2, -1, and 1/2. And in fact, that corresponds to this polynomial factoring to be x plus 2, x plus 1, and 2x minus 1. You may wonder, where did I get these are the actual roots from? You have to do more arithmetic. You can either plug them in, or you can do synthetic division or some other process you may have seen previously. If you haven't seen synthetic division before, don't worry. We'll go over it. For now, it's a more efficient way of checking something like this, but you can just plug them in. Okay. All right, so I would like then you to do the following. I'm going to give an example. I want you to write down all possible potential rational roots using the rational root theorem. Okay? I'm going to erase this again. All right. Let's write given an example. 5x cubed plus 12x squared plus 14. And what are the possible rational roots by the rational root theorem? So again, pause, work it out, what you think they are, and then resume when you're done. All right, so pause now. All right, so we have x equals p over q. X equals possibly then, well, our p's have to divide 14. Our q's have to divide 5. The divisors of 14 are plus or minus 1, plus or minus 2, plus or minus 7, and plus or minus 14. Notice, unlike our earlier examples, we got numbers other than 1, plus or minus 1, and plus or minus our number. That's because 14 is not prime, right? In our earlier examples, 2 and 3 were small primes. So we've got more divisors this time, more numbers that divided even. Right. In Q, though, Q is still prime, so I'm going to be 5 is prime, so there's nothing fancy happening there, rather. So possible values for Q are plus or minus 1 and plus or minus 5. So now, put that all together, and our possible potential roots here are plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14, or the same things but with 5s in the denominator. So plus or minus 1 over 5, plus or minus 2 over 5, plus or minus 7 over 5, and plus or minus 14 over 5. So that's what we get from the rational root theorem. Think for a moment, are there any of these we can rule out immediately that are not actually, cannot be roots of this polynomial, that cannot be solutions to this quantity being 0? If you want, feel free by all means pause the video and then think about it. All right. Here is the thing we're going to notice. All of the coefficients here were positive. I really assume sometimes I should say non-negative because there's no 0x, there's no term for x here, right? There's really a 0x. But all positive or 0, which means if I plug in a positive x value, this quantity has to be positive. I'm adding up a bunch of positive numbers. I'm adding up a bunch of positive numbers. So the solutions here, the potential solutions, which were positive, can't possibly work. So in this case, we could only need to check the negative values. That wouldn't be the case if I'd say negative here or something like that. But in this case, that's all I need to check. And I would like to do one more thing here, then given this, which is I'd like to convince you that the square root of 2 is irrational. Since you probably were young, maybe 6th, 7th grade, people told you irrational numbers existed. Maybe you took that on faith. But maybe the mathematicians were lying to you. We actually lie about a lot of stuff. Like the number 14 doesn't exist. It really goes 11, 12, 13, 15. Or did I just lie to you now? I don't know. We might lie. But I will convince you, hopefully, that we haven't been lying when we claimed that the square root of 2 is irrational. Let's see if we can convince ourselves that the square root of 2 has to be irrational. That is, it's not a rational number. So let's assume, here's the claim. Claim. Square root 2 is irrational. All right, so let's think. By square root 2, what do we mean? All right, 5 plus 3. By square root 2, we mean x such that x times x equals 2. That's what we mean to be the square root. All right, and that's the same thing as saying x squared equals 2. X squared minus 2 equals 0. So let's assume that there is such an x and it's rational. So x is rational. So x equals p over q. This is a polynomial, right? I can do the same trick. We can use the rational root theorem. P must divide. I'm looking now just at the polynomial, not at the equation, but the polynomial x squared minus 2. P must divide 2. Q, well, there's a 1 in front here. Q better divide 1. So our possible roots, potential rational roots. If I'm a rational number, I need to be plus or minus 2 over 1, or, so x equals plus or minus 2 over 1, or x equals plus or minus 1 over 1. So my possible values are plus or minus 2 and plus or minus 1. I can now plug those values into here and verify that none of them make that polynomial 0. 2 is here. 2 squared minus 2 is 2. Which is not 0. Same as I plug in negative value. And for plus or minus 1, same thing. 1 squared minus 2 is negative 1. Hey, that's not 0. So all 4 of these possible values are not roots of this. So this really has no rational roots. So the idea that there's an x such that x squared equals 2 and x is rational cannot happen. So square root 2 really is irrational. We haven't been lying to you, at least about that. All right. Now, one number you might wonder about that you've probably heard about before, often used an example of being irrational, is pi. Can we do this with pi? We're thinking about it. If we could, we would need a polynomial such that pi was a 0 of that polynomial. And that polynomial would have to have integer coefficients. And then we could play this game. There's a problem. It turns out, and it's actually a very deep mathematical result, that pi is not the root of any nice polynomial. And you need to make that a little more precise, but the idea is it's called a transcendental number, which is a number that is not the root of any polynomial with integer coefficients. So proving pi is irrational is actually quite tricky and difficult. The ancient Greeks were able to prove that square root 2 was irrational. You can use the same method if you want to prove that square root 3 is irrational, or square roots of any non-square positive integer are irrational. But it wasn't until like around the 1700s that people were actually able to prove that pi is actually irrational. So there's really something much more subtle going on there. But at least we should be convinced that square root 2 is irrational. All right, have a good day.